Right, in this video we're going to have a look at some more limits of trig functions examples. So this is our first one. We asked to evaluate the limit as x tends towards pi over 4 of cos 2x over cos x minus sin x. Now in this particular example, we're going to need to use one of our double angle formulae. Now we haven't used them much up until this point, so I'm going to use this example just to introduce their use. Now if you go back to one of the previous videos where I've introduced the double angles, then you will see that cos 2x, cos 2 of an angle, let's say 2a, just to generalize, can be written as cos squared of that angle minus sine squared of that angle. That's one of the double angle identities. And I'll show you in this example why we choose that one. So what I'm going to do is I'm going to replace cos 2x. So let's do that. I've got the limit still. Don't forget to keep writing the limit until you've actually found it. And I replace cos 2x with cos squared x minus sine squared x. And then again in my denominator, I've got cos x minus sine x. Now again, I can't do anything yet, but do you see that I can now factorize what's in my numerator? I haven't found the limits, I've got to write it again. I can factorize that to get cos x minus sine x. It's a difference of two squares, so I have cos x plus sine x. Write my denominator, cos x minus sine x. So the reason why we chose that particular double angle identity is so that we can now factorize and cancel. So you see the cos x minus sine x in the numerator cancels with the same expression in the denominator. So what we have here is we're now working out the limit as x tends towards pi over 4 of cos x plus sine x. Now remember, straightforward limits, you can just substitute the value of x in, provided you don't land up with a 0 in your denominator and you don't land up with, for example, infinity over infinity. So let's sub our x in place of x. So we've got cos pi over 4 plus sine pi over 4. We've actually found the limit now. That's why I don't have to write limit anymore. Think back to your special angles. Cos pi over 4 is root 2 over 2 plus sine pi over 2 is also root 2 over 2. So in my numerator I now have root 2 over 2, which is 2 root 2, and my denominator is a 2. Cancel those 2's and I'm left with root 2. So that's one particular example where we needed to use our double angle identities in order to simplify further by factorizing. Let's look at another example. In this example, we asked to evaluate the limit as x tends towards 0 of x squared times by sine 1 over x. Alright, so let's start. Now we know that we've got a very important limit. We know that the limit as x tends towards 0 of sine something with an x, could just be x on its own, divided by that same angle is equal to 1. So we know that to be true. And I'm going to show you in this example how we're going to use that. We can't immediately sub x to be 0 because we're going to have sine of 1 over 0. So we need to maybe try and use this guy on the right. So we want to use that in order to make our limit easier. Alright, so at the moment we've got limit of x squared times sine 1 over x. So if we use that limit on the right, I need sine of something. At the moment I've got sine of 1 over x. So in my denominator I actually need a 1 over x. So I'm going to create that. So I'm going to put my sine 1 over x here, sine 1 over x, and I want to be able to divide by the same thing. I can do that provided I also multiply by that 1 over x as well, because I've multiplied by 1 over x and I've divided by 1 over x. But don't forget that you still have an x squared. So what we actually have here is we have the limit as x tends towards 0 of sine 1 over x over 1 over x. And then 1 over x times x squared is just x, so it's times by x. Now one of the properties of limits is that the limit of the product is the same as the product of the limits. Meaning if I have the limit as x tends towards 0 of a function times by another function, that is the same as the limit of the first function multiplied by the limit of the second function. So this is a property that we're going to use often when we're working out limits. So here, scroll down a bit to create some more space. So here what I have is actually the limit as x tends towards 0 of sine 1 over x over 1 over x multiplied by the limit as x tends towards 0 of x. Now we know from this guy up here, from that guy there, that the limit of my first factor here is going to be 1 times by the limit of x as x tends towards 0. I just replace that x with 0 is 0. So 1 times 0 is 0. So overall my limit is 0.